So I've been using Blender for about a decade now, but just in the last 2 years, my love for Blender has really grown to new heights, and that's mostly because of geometry nodes. Geometry nodes are similar to coding in a lot of ways, but instead of writing text, you plug different types of nodes into other nodes to do things like create simple geometry, scale, rotate, and move things around. Geometry nodes are powerful tools that you can use to build some really cool stuff. I've had some other geometry node projects in the past couple of years, including a Minecraft terrain generator and a galaxy generator, which each had some unique development challenges and stories of their own, but by far my most time-consuming and complex project to date is Engine Generator. This project came about because I wanted to push my limits with geometry nodes and make something really complex and intricate. I also love cars, so I knew it would be a perfect fit for a project. So comparing how many nodes these projects have gives an idea of the scale of what's going on behind the scenes. And if you'll join me, let's go on a journey and take a look at the Engine Generator close-up. Just so we're on the same page, engines, or more specifically internal combustion engines, work by converting pressure created by igniting fuel into rotational force that can be transferred to wheels, propellers, or whatever else you need to power. While there are definitely a lot more components that are needed to run an engine, there are 5 main parts that we'll focus on. Pistons live in a sealed chamber called a cylinder and are pushed up and down by the explosions inside an engine. The connecting rod moves along with the piston and connects to the crankshaft, which converts the up and down movement of the piston into rotation. And in order to get explosions to happen in the cylinder, you need to bring fuel and air in and then get rid of the used up mixture. And this is where the camshaft comes in. The camshaft is driven by the crankshaft via a belt or a chain. It rotates cam lobes, which are specially shaped to open valves in the cylinder at specific times. There are 2 types of valves for each cylinder, intake and exhaust. To see these valves in action, let's take a look at the 4 strokes to operate a 4-stroke engine. So the first stroke is where the cycle begins, and it's called the intake stroke. The camshaft rotates the cam lobe, which pushes the intake valve open as the piston is moving down, which pulls air and fuel into the cylinder. Then for stroke 2, called the compression stroke, the intake valve closes and the piston moves back up, which compresses the air and fuel into a small space at the top of the cylinder. Then the combustion stroke comes next, and that's where the spark plug ignites the mixture, which then forces the piston back down. And finally for the exhaust stroke, the camshaft opens the exhaust valve as the piston begins rising back up to the top of the cylinder, and the spent mixture is then forced out of the cylinder, allowing for a fresh start when the cycle happens all over again. And this cycle happens really fast, usually between 20 and 200 times per second. So pretty much all the footage you'll see of the engine and engine generator, if it was moving that fast, you wouldn't be able to see it, so it's slowed way down. Alright, so now let's get back to Blender. Engine Generator is built from the ground up in geometry nodes, and I wanted it to be as accurate to a real 4-stroke engine as I could make it. I also wanted to give user control to as many aspects of the engine as possible via node input, of which there are over 70. Over the course of around 700 revisions, 3 months, and hundreds of hours of development, Engine Generator changed quite a bit. So obviously, just given the scale of everything, I won't have time to break down exactly what's going on with all the nodes, but I'll do my best to summarize the development process, and hopefully you'll find something interesting along the way. Pistons are one of the most recognizable components in an engine, and so that was the first thing I added when I started working on Engine Generator. Pistons move up and down continuously while the engine is running, so I started by using a sine wave to replicate this movement. So let's take a look at this simple node setup, which creates a simplified version of a piston moving up and down. And it might be a bit easier to understand what's happening here if we take a look at the values that each node is processing and outputting. So there's a scene time node, which allows you to use seconds as a value to drive movement. And then that value is multiplied to allow you to control the speed. And then that's plugged into a sine node that creates the wave, which is then plugged into a combine XYZ node, which isolates to a single axis of movement, in this case the z-axis or up and down. And then that whole thing gets plugged into a transform geometry node, which takes the mesh of the cylinder and then moves it. So while this is a good start, it has several issues, not least of which is the fact that I'd have to copy and paste the entire chunk of code if I wanted to add multiple cylinders and then manually change the position. which even for something so simple can get out of hand pretty quickly. So I need a better method to add multiple pistons. The solution to this problem, and one of the backbones of the engine generator, is the repeat zone. So using this node allows everything within the zone to be repeated a set number of times. And the real power of this node is unlocked when we increment a number every time the loop runs. So this basically lets us set an index, or sort of like an address or an identifying number, which is specific to a certain loop. And then we can use that to change an individual loop separately from all the others. To demonstrate this, I have a repeat zone set up with a few options to interface with. I can set how many cubes there are, and I can also select the index of the cube I want to change. So you notice as I change the index, the selected cube turns red, and I can then rotate the cube to whatever value I'd like. The functionality here has a lot of potential. You can not only rotate and change color, but also scale, move, and otherwise manipulate isolated parts of your project. To apply this to our engine, we can use this to make as many pistons as we want just by changing how many times the loop runs, and then we can separate them from each other. And we can also change the timing so that they don't all move up and down at the same time. They're moving out of phase of each other. Obviously, we'll need more than just pistons, so I added a crankshaft next, which again is the part of the engine that transfers the up and down movement from the piston into rotation that can eventually be transferred to wheels and stuff. The piston and crankshaft need to move in sync with each other, but one of the challenges is that one type of movement is up and down and the other is rotational. But thankfully someone had already figured out the math for piston movement, so I was able to use this formula, and by packing it into a node group, I can calculate the piston's vertical position by inputting just a couple variables, including the rotation of the crankshaft. Now the piston moves up and down, corresponding to the crankshaft's rotation, which means we don't have to use the old sine wave method. So now we have a solid start to the engine, but we still need a way to connect the piston to the crankshaft so that they aren't just floating around, and that's where the connecting rod comes in. Again, it transfers the movement of the piston so that it goes to the crankshaft. So this was another challenge because it also has a unique movement that needs to be related to the rotation of the crankshaft and the up and down movement of the piston at the same time. And so it needs to move in a way so that it stays connected to both. And this is where Blender just gets really fun and exciting. I just love taking a problem and then figuring out what you know and what you don't know, and then breaking it down into smaller chunks. It's a lot like solving a puzzle. You try different puzzle pieces together, and some of them don't work, but when it does, it's just really cool to see it come together. It's just really satisfying. And figuring this out was one of those moments. I took the top of the connecting rod and then basically anchored it to the location of the piston, so that as the piston moved up and down, the rod went with it at the rotation point called the wrist pin, and then I can rotate it around that anchor point, and then I can figure out the exact amount it needs to be rotated by basically solving the triangle that's created between the crankshaft, the crank pin, or the part of the crankshaft that is offset from the center, and also the origin point of the piston. So because we already have one side length and its corresponding angle, and the length of the missing angle side, we can use the law of sines to solve for the missing angle, which you might remember from your high school math class. So up to this point, we have a pretty decent representation of the core of an engine, but we're still only limited to inline engines, where all the pistons are in a line. But as you probably know, not all engines have a single row of cylinders, so an engine like a V8 has multiple banks, so you can fit more cylinders and get more power while still keeping the engine short enough to fit in a car's engine bay. So to add more banks, I put the piston and rod in a repeat zone to give each cylinder bank its own index, and then I can use that to individually control the timing of each bank. And this is crucial because if the timing isn't adjusted based on that angle, then the piston and crankshaft won't move in sync anymore. And this is just another example of how useful repeat zones are. So the engine's coming along nicely, but we're still missing the other two big components, the camshafts and the valves. As we covered, these control the four strokes of the engine by allowing air and fuel into the cylinder and then letting it back out again once it's been ignited and used up. In a lot of ways, the movement of the camshafted valves are similar to the pistons and crankshaft. One rotates and the other moves vertically. There are some major differences though. For one, the camshaft rotates at half the speed of the crankshaft because the valves only open and close once for every 2 rotations of the crankshaft, which is an easy problem to solve since we can just divide the rotation of the crankshaft by 2 to rotate the cam. The second major difference though is a little more impactful because unlike pistons, which are constantly moving, the valves need to stay still part of the time when they're closed until the camshaft lobe rotates around and pushes that valve open. So this means that the system used for the pistons won't work for the valves, at least not without some modification. So my first solution to this problem was to go back to a sine wave for movement, and in order to keep the valves from moving until the proper time, I made a node system that only allows the sine wave to move the valves if the camshaft is within a certain rotation range. One of the challenges with this is that the sine wave has to be scaled correctly, but putting this into a repeat zone and duplicating it allows for a dual overhead cam system, and just like the crankshaft and pistons, you can adjust the timing individually, so you can have a separate camshaft controlling the exhaust and the intake valves. So there's a couple issues with doing things this way. First of all, a sine wave doesn't really represent the movement of a valve very well, especially when I wanted the size and shape of the valve to be adjustable. And although you can scale a sine wave vertically so that the valve opens a smaller amount, and there are functions you can use to shape the curve of a sine wave, it gets really complicated to transfer a 2D wave to a 3D shape and then control it in any specific way. So in short, the movement of the valve and the cam's rotation and lobe shape were just approximations and weren't really accurate to the real thing. But thankfully, Geometry Nodes has an incredibly useful node that can measure distances between meshes called the raycast node. I like to think of a raycast as sort of like a tape measure where you start at a point and then it casts a line in a direction until it hits something, and then it just measures how far that line is. To implement this into a camshaft system, I put the raycast at the center of the cam and then pointed it towards the tappet, which is the part of the valve system that the cam lobe actually physically touches. The mesh of the cam lobe rotates along with the camshaft, and as it rotates, the raycast is measuring that distance from the center of the camshaft to the face of the camshaft lobe. So if the measured distance is greater than the radius of the camshaft, then that additional distance is then sent to the valve, which is used to move it up and down. And the result is that the valve moves almost perfectly in relation to the rotation of the cam, which is a huge improvement over the old system. But the big problem with this is that the ray has no volume, so it's only an infinite small slice of space. And because the cam and tappet have volume and they have a width, if you only have a single ray, then the movement will follow that single slice and the mesh will clip. So like this, it's not exactly accurate or ideal, even though it's a step in the right direction. But to solve this problem, I used repeat zones yet again, and it allowed me to create an array of rays that can be fit inside the area of the tappet. So I can just basically set a bunch of rays in that area, and then I can compare the current iteration to the last iteration, and so the output will be the greater of the two values. And as long as you have enough rays, the result is smooth and accurate, and it looks really good. And it will also adjust accordingly, no matter what the shape of the cam lobe is. And you can have some pretty interesting, crazy combinations that would never really work in a real engine, but I think it just looks cool, and it's really satisfying to see it work so well, especially given how janky the old system was. So it started becoming pretty obvious that I need some sort of more complex timing system to control the way everything moved together as a whole. So in an actual engine, the movements of components follow a specific order called the firing order, and that's so that the engine stays balanced and can dissipate heat efficiently. And this proved to be one of the more challenging aspects of the whole project because every component needs to follow this order, but it does so in its own way, kind of like we talked about earlier. It's a bit like an orchestra, where each instrument is playing along to the song, but it's doing so in a unique way that's contributing to the greater whole. And the sheet music will look different for every instrument. I had a couple early methods that I developed to get this to happen, but for the final product, it uses a system that basically takes all the inputs relevant to the firing order and then it can calculate the other missing pieces, so it knows how far each component should be rotated based on its index, and it basically just sends those angles out to each component as needed. But things get more complicated when there's multiple banks because there's more factors involved. So you have things like the angle of the banks and whether or not the row of cylinders fires immediately. So like a V6 where it fires back to back, or like a V8 where it is offset a full 360-degree rotation of the crankshaft before the next cylinder fires the next bank over. And so because of all the factors involved with multiple banks, I wasn't able to give the user full control over all the cylinders. So you can set the main bank firing order and then change the variables that affect the other firing orders like the bank angle and stuff like that. So I also implemented an automatic timing mode, so you can let the system preset the relevant variables based on the engine size. And it basically just uses a set of switches, so it compares how many cylinders you have, and then based on that it will let certain inputs pass through and then stop others from passing through. There are so many things I didn't have time to cover, but I thought they were really interesting to work on, so I thought I'd mention them here. You have things like the valve springs, the visualization of the stroke for each cylinder, the timing belt and chain, the belt chain tension, valve collision detection, the error detection system, displacement calculation, separate crank pins, scaling parts of the mesh separate from the whole, rotating individual rows, and on and on. There's a lot of these systems, and some of them took weeks to develop. Even something that seems simple, like the rotation of the valves, can be a huge pain in the butt because there are tons of tiny compounding transformations, and it takes a lot of behind-the-scenes nodes to work. Just like math, geometry transformations have an order of operation, and things don't work right if you get certain transformations out of order. A lot of node groups are interdependent, so everything needs to work together or things fall apart quickly. So there is one system that ended up being one of the most complex, but also the most rewarding to develop. And this will be the last one I cover in today's video, and that is the firing order calculation and display system. So on its surface, figuring out which cylinders fire in which order seems pretty simple. On a human level, all you have to do is look at an animation of the engine, and then you can see which cylinders are moving and firing in which order, and then you just write that down and that's your firing order. But getting the geometry nodes to know this was a lot more complicated. Figuring out the firing order for an inline engine is pretty straightforward. You just take the main bank firing order and then that's it, like that's your firing order. But as we've already seen, multiple banks get a lot more tricky because there's a lot more factors involved. I wasn't even sure how to go about adding a feature like this, just because there's pretty much infinite ways to adjust the variables involved in that. So after thinking through the information that I realized that I had all of the variables that affect the firing order, and I had an index that allowed me to isolate individual cylinders. And so if I could somehow calculate those two things together, I could figure out the specific angle that every cylinder fires at, and then I can just rank those from smallest to largest, and that would be the firing order. So implementing this is a lot more complex because there's a lot of nodes involved. So I developed this kind of scary looking waterfall system that can compute all of that required data. There are 1,722 nodes involved in this process, which is close to 40% of the total node count for engine generators. So that gives you an idea of how complicated this gets. But a lot of that is due to inefficiency because of limitations with repeat zones. All that to say though, the process is a set of relatively simple steps that are just repeated over and over again. To get a better idea of what's happening, let's take a look at figuring out the firing order for a V6. So we have the following variables involved. We have 2 banks, we have 3 cylinders per bank. Our main bank firing order input is set at 1, 2, 3. We don't offset to the next stroke, so we don't have a 360-degree delay before firing the next bank over in the row. The firing interval is just set to the default, which you can change in the node controls. The default is just 720 degrees divided by 3, so 240 degrees. This is just the angle of crankshaft rotation that happens between cylinders in a bank firing. The bank angle is 60 degrees and the rotation direction is clockwise, which is standard. So if it's counterclockwise, the firing order is just reversed. So with this information, as well as knowing the index of all the cylinders, we can figure out the firing order. So again, even though there are a total of 6 cylinders in a V6, we only get direct control for the firing order of the main bank. And since that bank has 3 cylinders, all the other banks inherit the main bank's firing interval. So they all have 240 degrees of separation, but they also get their own timing adjustments based on the bank that they're in. We need to figure out which row each cylinder is in, and I call this the row index. It's a number that defines the position a cylinder is from the front, and we can calculate it with this formula. So the row index equals the cylinder number minus 1, and then we do modulus cylinders per bank. If you're wondering what a modulus is, it's basically just the remainder A divided by B. But you can think of it, for the purposes of this video, as just wrapping around after you've reached a set number. So like let's say we have modulus 4. Once we get to 4, it wraps around again. So 4 modulus 4 is 0. But 5 modulus 4 is 1 because it's wrapped around again. So 4 goes into 4 once, and then the remainder is 0. So let's plug those variables in for every cylinder and use the formula to determine the row each cylinder is in. For our V6 engine, here is what the row indexes look like. The front row has an index of 0, the middle row has an index of 1, and the back row has an index of 2. And the reason it's from 0 is because it's the distance from the first position. So the front row is in the first position, so it's 0 away from being first. So now our system has part of the information it needs, but we still need to apply our firing order input. In our case, this doesn't change anything for the V6 since the input is just 1, 2, 3. But if it was some other order, the system needs to be able to factor that in. We can use the row index that we calculated and then use that as a map to map it onto the firing order input. So index 0 gets mapped onto the first firing order number, index 1 gets mapped onto the second, and so on. So this will allow the timing system to factor in any user input. And for example, if we had, say, 1, 3, 2 as an input, our main bank firing order would just get mapped onto that instead, and it would look like this. Now we have some more information on which cylinders fire in which order, and we can do some more math on it to figure out the specific angle of the crankshaft that those cylinders fire on. So we just take that processed value and then multiply it by the firing interval. Here's what that looks like when we plug in each cylinder's processed row index. We still don't have the full picture yet since we haven't factored in any timing differences based on which bank a cylinder is in. So first, we'll need to figure out the bank index for each cylinder, and we can determine this with the formula. Bank index is the seal, or rounding up to the nearest integer, of the cylinder number divided by the cylinders per bank minus 1. So now with that calculation out of the way, we now know which bank each cylinder is in, and we're one step closer. Going back to a diagram of the engine, these cylinders are in bank index 0, and these cylinders are in bank index 1. Now we can also plug our variables into the formula for each cylinder. We take the bank index and multiply it by the combined total of the bank angle, which is 60 degrees, plus the stroke offset, which is 0, plus the separate crank pin angle, which is also 0. Once we calculate that out, we're left with the firing angle adjustment based on the bank. Cool, so now let's put it all together and find the firing angle for all of the cylinders. We take the firing angle per row and add it to the firing angle per bank, then do mod 720. None of our V6 angles are above 720, but that can definitely happen based on configuration, so it needs to be factored in. When we plug all that in and math it out, we get the final angles. Now the last step is to compare all the angles, then rank them from smallest to largest to find our firing order. When we do that, we get 1, 4, 2, 5, 3, 6. Now the nodes have successfully found the firing order. And this process applies to any configuration of banks and cylinders, but just due to the exponential increase in comparing the firing orders, there is currently a 16-cylinder limit. You can still have configurations beyond that, I just can't tell you the firing order, but maybe I'll go back and fix this in a later update once Blender adds some more features. So there you go. There's a brief overview of how the engine generator works. It was definitely up there with one of the most challenging, technical, and sometimes really frustrating things I've ever done, but it was really rewarding to see it all come together. And honestly, as I've been making this video, just getting to mess with it again about a month after I finished it was just really cool. It's just really satisfying to see it all work. Pretty proud of how it turned out. Engine Generator is available for purchase through the link below if you'd like to try it out for yourself. It supports my work and future projects. And you can use the discount code HOWITWORKS for 10% off. I really appreciate you watching. Hope you have a wonderful day, and I will see you in the next one.